morning, students. Today I'm doing a quick review of differentiation. It's not meant to replace what we learned first semester, but it is meant to refresh your memory. If there's something that you need to go back to, please refer to your notes from first semester. So the first thing I wanted to review is these are the derivatives that people tend to forget. So I wanted to make sure that you'd gone over these at least one more time. The derivative of e to the x, everyone pretty much always remembers that one, is e to the x. But the derivative of any other number to the x would be that number to the x times the natural log of that number. This actually also works with e to the x because natural log of e is 1. So you could just memorize that one if you want to, but that's the one people tend to forget. For unnatural logs or logs that are not base e, that's the derivative of that is 1 over x times natural log of a in the denominator. And then the other ones that people tend to forget are the trig inverse derivatives. So those are some to study. The sine inverse derivative is 1 over the square root of 1 minus x squared. The derivative of tangent inverse is 1 over 1 plus x squared. And the derivative of secant inverse is very weird, and I hope it's not on your test, but it's the absolute value of x, 1 over the absolute value of x, times the square root of x squared minus 1. So those are some derivatives that people tend to have a need to review. You're likely to see implicit differentiation, or I would have said that anyway any other year. I don't know if you'll see it this year, but for implicit differentiation, remember you treat y like a function as you're doing your derivative. And so in this example, this part would require some product rule, making sure that you have negative 5x as one of your functions and y as the other function. And then in this part, there would be a chain rule. So as I take this derivative, I would get 6x squared. We treat x normally when we're doing implicit differentiation. And then plus, or I can do minus, but then I need parentheses, so I'm going to say minus 5 times y left alone plus 5x times dy dx minus 2 times y to the 1 power times dy dx. And that's not a tick mark, that's a first power. And then equals 0. Your next step would be to solve for dy dx, but that's the idea with implicit differentiation. The idea with second derivatives is you would do your implicit differentiation to begin, and then you would take a second derivative. But when you take the second derivative, you are also going to treat y like a function and treat dy dx like a function. So I would take my first derivative here. I would say 4, not a pen. I would say 4y to the third power times dy dx minus 2 equals 0. I would solve for dy dx, so I have dy dx equals 2 over 4y cubed. I would reduce as much as I can, so I would make this a 1/2. And then when I take my second derivative, this is handy, I don't have to use the quotient rule here because I can just say 1/2 y to the negative third power. So when I take my second derivative, I still treat y like a function. So I would bring down the negative 3. So I have negative 3/2 y to the negative fourth times dy dx. But at this point, we know what dy dx is because we did that over here. So we'd replace dy dx with this number. This is a rough sketch. If you need more, please ask. The derivatives of inverses, I really highly doubt this will be on your test, but this is the one that says that if you've got an x, y on a function, then y comma x is on the inverse, and the two slopes, oops, I forgot a tick mark here, the two slopes are reciprocals of each other at that point. Notice these are not the same x coordinates, they're corresponding x coordinates. So if g and h are inverses, if I want to find, what am I trying to find here? I'm trying to find h prime, so the inverse prime at, let's say I'm trying to find it at 3, I bet I would do. So h prime of 3, the x coordinate on h is 3. Actually, I'd be trying to find h prime of 1, sorry. If I'm trying to find h prime of 1, I know that that's going to be 1 over g prime of 3. Because 3 comma 1 is on g, so that means that 1 comma 3 is on h, and that means that those are reciprocals of each other at that point. So h prime of 1 would be 1 over negative 2. Anyway, I doubt this will be on your test this year, but normally it's 1 point on your multiple choice. Mean value theorem is the one that says that your slope of your tangent line is going to be equal to the slope of your secant line on some interval as long as your function is differentiable. The key point on this is please make sure that if you're going to use the mean value theorem, you don't have to remember the name of the theorem, although you can say the name of the theorem, but please remember that you say that you are allowed to use the mean value theorem because you have a differentiable function. So either they'll tell you that f is differentiable, or you'll be able to figure out that f is differentiable from the information that they gave you. But please state that if you're going to be using the mean value theorem. The mean value theorem does not apply if you have a corner. There's no secant line that has the same slope. There's no tangent line that has the same slope as that secant line because there's a corner in between the 2 points. Another thing you'll likely see is that relationship between position. So the relationship between position, velocity, and acceleration. One thing, speed is the absolute value of velocity. So if they ask you whether the velocity is increasing, that's not necessarily the same thing as speeding up. Velocity is increasing just means positive acceleration. Speeding up will mean that your velocity and acceleration have the same sign. Similarly, if they say moving right or left, that's just the sign of the velocity. But moving towards the origin, it depends on your position as well as your velocity. Velocity tells you right or left, but if you are already to the left of the origin, then moving towards the right would be moving to the origin. So those are some things to make sure you're thinking deeply about those questions when you are answering those. But the derivative of position gives you velocity, the second derivative of position gives you acceleration, and if you go backwards, you need to use integrals. The other thing we really use derivatives for a lot is the finding extreme values, and this would be either in a story problem kind of situation, which is called optimization, or just in a general situation about finding extreme values for a function. There are 3 ways to do that. There's the candidates test. The candidates test would be on a closed interval, and it would be looking for the keywords that you're going to use. The candidates test would be the absolute max or min. If you're trying to find an absolute max or min, then you should be comparing y coordinates. The candidates test is the one where you find all of the critical points and you find the end points, and you just test all the critical points and the end points in your function, and you're comparing y coordinates to see which one is the biggest. Okay. The way you find a critical point is you look at the derivative is either does not exist or the derivative is equal to 0. And those would give you your critical points. You plug all of those x coordinates into your function and compare the y coordinates. That's the candidates test. The first derivative test is the one where you make a number line. And your number line is for the derivative. You have an end point. And then any critical points, which you find this same way by either setting the derivative equal to 0 or does not exist. Oops, I called the critical point C. And for the first derivative test, you're looking at sign change on your derivative. If you need to justify an answer with a first derivative test, you would say there is a maximum at x equals c because f prime changes sign from positive to negative. Really try to avoid words like it. Try to avoid words like the function or the graph or the equation, because derivatives and f prime and f of x are both equations and functions and derivatives. So you really want to be clear about which one you're talking about. Are you talking about f or are you talking about f prime? The second derivative test is also for finding extreme values. This is different from the definition of concavity and critical and inflection point. Second derivative test is for finding extreme values, so you still need to have your first derivative equal to 0. Second derivative test doesn't work if your first derivative doesn't exist. So your second derivative test means that f prime is equal to 0. And then there are two possibilities, well actually 3 possibilities for the second derivative test. One possibility is that f double prime at your critical point is positive, and that would mean that you have a concave up function and a horizontal tangent line, so that would be a minimum. And then the other possibility is that the second derivative is negative, so that would mean that you have a concave down function and a horizontal tangent line, so that means that you'd have a maximum at x equals c, your critical point. And then the third possibility is kind of a sad one. It means your second derivative is equal to 0, and that means that you can't use the second derivative test. You have to go back and use either the candidates test or the first derivative test. Local linearity and linearization is another topic. Remember, linearization is just using the tangent line. So it looks like a whole new equation, but it's just the tangent line. If you ever have to write a tangent line equation, you always need 3 things: x coordinate, y coordinate, and slope. X coordinate is here. Y coordinate is plug it into the function. Slope is plug it into the derivative. So that's just what local linearity means. It means we're going to use the tangent line to estimate this function. I wrote it in this weird way because usually we write it backwards because that looks more like point slope form. But the reason I wrote it this weird way is because if you look at it closely, that's a Taylor series of degree 1. Did I just blow your mind? Anyway, that's a review of derivatives. I talked fast because I only have 15-minute limit, and look, it's 14 minutes long. All right, have a good day.